Welcome back to Power Series on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we're going to do a second example using Power Series to determine the interval of convergence. And here is our series up here at the top left, the series from n equals 1 to infinity of the quantity x minus 6 raised to the n power divided by n to the n power. Again, normally the best test to use to determine the limit L is going to be either the ratio or the root test. Now in this case, it's pretty evident that we need to use the root test. Might be easier, just because every single term here in the numerator and denominator is raised to the n power. When you have that satisfied, it's usually easiest to use the root test. It tends to make it a lot simpler. You could use the ratio test, but it just requires more steps. Alright, so let's calculate the limit L. Alright, so the limit L is, the limit as n goes to infinity of the quantity x minus 6 raised to the n power over n to the n power, and notice I have my absolute values here, and the root test says to find the limit, I take all of that and raise it to the 1 over n power. And notice what that does effectively is it cancels both powers of n. So all I'm left with is the limit as n goes to infinity of x minus 6 over n. Now, remember that the x minus 6 component is not a function of n, so that term I can actually pull out in front of the limit as long as I remember to keep those absolute value signs. So the limit is the absolute value of x minus 6 times the limit as n goes to infinity of 1 over n. Now, we can straight up evaluate this limit here. What's the limit as n goes to infinity of 1 over n? Well, if you just plug in infinity in the bottom, you get 0. So, the absolute value of x minus 6 times 0 is 0. So, I don't care what value of x is. I don't care if it's positive or negative. Even the absolute value times 0, the whole limit is 0. And remember, what we have to do is set the limit to being less than 1. Well, 0 is not a function of x. In fact, because you multiplied this x term, so to speak, by 0, it effectively makes this limit not even a function of x. It's just 0. 0 is 0. It's not anything else. And 0 is always less than 1, right? It's always less than 1. So if you ever have a case where the limit, for whatever reason, turns out to be one number, and normally that number is 0. That's just normally how it turns out. 0 is always less than 1. It's less than 1 for any value of x because 0 doesn't even depend on x. Let's say x is 1,000,000. Well, 0 is just 0, and 0 is always less than 1. So this is a really easy case. So when you have 0 less than 1, you don't have to find any endpoints. The reason you don't have to find any endpoints is because 0 is always less than 1. So this power series converges at every single value of x, because this is satisfied for every single value of x. 0 is always less than 1. In other words, our radius of convergence is infinity. It converges for every single value of x, which means that our interval is simply from negative infinity to positive infinity. So if you ever have this limit and it goes to 0, you pretty much don't have to do anything else. You just say radius of convergence is infinite and the interval is from negative to positive infinity. No finding endpoints because there aren't any, and you don't have to check them because there's none. Okay, so this was actually a really easy case of finding interval of convergence for a power series. It won't be a common type of problem, most likely on your exam, but it at least shows you one case where this does happen. When we start the next video, we're going to do a third example, which is, again, about as difficult maybe as the first one we did. So one of the harder problems that has all three of these steps. Join us in that video, but please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.